Recording is on.
Hello, everyone. Thank you for attending to the fourth Deeptails seminar. Today, it is my pleasure to welcome and to introduce you to Edoardo, Cetin, and Oya Celiktutan. Probably I didn't pronounce this correctly. I'm sorry for that. So Edoardo is a PhD in machine learning at King's College under the supervision of Oya, who is an assistant professor there. And we are very happy to have them here because it's the first Deeptails seminar in which we are going to discuss some robotic things. And I am particularly happy about that. Today's talk is about observational imitation learning, or at least towards observational imitation learning. So, Edoardo, Oya, the floor is yours. Thank you for accepting the invitation. And we are really looking forward to hear what you have to say.
So, hello, everyone. Thank you so much for inviting us today. So, under normal conditions, we would come to Grenoble to give this seminar because we both like skiing a lot with Edoardo, but hopefully next year. So we are really happy to talk about our work on observational imitation learning today. So first, I will start by introducing the problem, and then I present the highlights of our approach to the problem, and then I will hand over to Edoardo, and he will be presenting the details of our approach. So here is our motivation. So as the robots are progressing from controlled lab environments to uncontrolled human environments, it is increasingly desirable that the robots develop higher levels of autonomy. And one of the things that we are interested in to make robots to learn from human behavior, either new tasks or how to interact with them by interacting with them and through deep reinforcement learning. So to achieving such task, particularly imitation learning has been very useful to equip robots with such capabilities. And learning from expert demonstrations can be divided into two categories. The first one is the behavior cloning, which is the traditional imitation learning framework, and which focuses on directly copying the observed behaviors. However, one of the weaknesses of this approach is that it requires manually designing a reward function. However, in most cases, designing a reward function is not possible. Even if possible, it highly depends on the creativity and knowledge of the designer. And also, once it is designed, it is fixed, and it is hard to adapt to novel contexts. So to address this weakness, another approach is the inverse reinforcement learning, which enables learning rewards from observed behaviors. However, most of the algorithms based on inverse reinforcement learning, they are agent-centric approach, meaning that often they require that the actions and observations should be collected from the agent's perspective. For instance, as shown in this figure, that we should have a human demonstrator who should guide the robot manually by hand to demonstrate the task in the agent's space. However, this leads to an unnaturalistic interaction, and this is also a time-consuming task and a tedious task for the user. On the other hand, humans are capable of learning by only watching others in most cases, and we want to make the robots to reach a similar capability, even the point where they can simply learn, for example, watching YouTube videos as humans do. So to address this problem, these challenges, there has been a growing effort in the area of observational imitation learning, which is also known as visual imitation learning or third-person imitation learning, which focuses on making robots to learn tasks by simply observing others. However, the main challenge is that making this work from raw sensory observations, for example, the images captured from the robot's cameras, is a significantly, extremely challenging task because there might be significant visual differences between the agent's domains and the expert domains, as well as the expert and agent might have different embodiments. So on this slide, you can see a glimpse of the related work in this area. So the early methods, they focused on designing handcrafted mappings to obtain some domain invariant features. But as we mentioned, this also has the limitations that we discussed before. But the later works, they focused on learning these mappings instead, but they also focused on some specific data collection setup from experts and agents perspective. For example, in this case, they focused on collecting data, assuming that they will be able to collect the demonstration for using multiple cameras from different perspectives. And then in this work also, it is assumed that even if minimal human supervision is available to indicate robot to success and failure cases. Okay, so our main contribution is actually in this area of the body of work, which is focusing on, which is a proposed for study et al. And then also adapted by Okamura et al. And the idea is actually here we would like to achieve this observational imitation learning without assuming such assumptions like multiple cameras or human supervision, and we would like to achieve this without relying on any specific features. These methods were successful, but they were only limited to low-dimensional control tasks, as you can see here, but also they did not really investigate the significant changes between the agents and expert domains. So in our recent work, we focused on extending these works, observational imitation learning, from low-dimensional control tasks to high-dimensional control tasks, while also making an algorithm robust to significant domain differences between the agents and the experts domain in terms of both appearance of the environment, but also the agent embodiments. And this is the algorithm that we propose, which is called DisentanGAIL, and which has been accepted to ICLR this year recently. And we will be presenting this work on the 6th of May, and you are welcome to attend our presentation at ICLR as well. So to explain the idea underlying the DisentanGAIL, I would like to talk about a bit of background. So our approach relies on the reinforcement learning and generative adversarial networks around GAN framework, and basically it has two main components. Similarly, in analogy with GANs, so it has two main components. The one component is the discriminator, and the second component is the policy, namely the generator. The whole idea is that the policy generates a sample from its current policy, and then together with this, with the human demonstration, this is given to the discriminator, which is trained to produce a reward function, and which attributes high rewards to the human demonstration and the low rewards to the policy samples. And then agent improves its policy to optimize the reward function and tries to make it harder to distinguish from the human demonstrations. However, particularly in our work, our work focuses on upon the methods which is called GAIL, proposed by Ho and Ehrman, which is called Generative Adversarial Imitation Learning. Here, the discriminator is simply a binary classifier that is trained to produce, in this case, pseudo rewards. So it does not really learn a reward function that explains the expert behavior, but instead it can learn the policies. But as I mentioned, this approach has been proposed for agent-centric imitation learning. So our goal is to actually to change this method, to adapt this method that it can work also observational imitation learning, where we collect actions and observations in the agents and experts their own spaces. And the input, for example, is again will be the sequence of images that you can see here. From these images, how we can create a discriminator, how we can design a discriminator such that it can just take into consideration to the information regarding the achieving a goal, but also it should not take into consideration the information regarding the visual differences between the agent's domains and the expert domain. So to achieve this goal, we divided the discriminator into two parts, as shown here. So the first part is the preprocessor, and the second part is the invariant discriminator. So the idea is that in the preprocessor is a network that takes the observation, the images, and then maps them to a latent space that only contains information about the goal completion, the progress to achieve a goal, but not the information regarding the domains, for example, the visual differences between experts and agents domains. And then the invariant discriminator takes its latent representations as input and then outputs the discriminator score for the observed behavior. And in this case, we particularly, this discriminator takes into consideration the latent representation of 4 most recent observations to better capture the goal completion progress through consecutive frames. But here is the question is how we can achieve a domain invariant space from the preprocessor's outputs. So here, the idea, the main contribution lies in this area of our algorithm. The contribution of our algorithm lies in this area. So particularly, we propose 2 novel constraints and then in their implementation. So the idea is we use another network to estimate the mutual information between the latent representations and their domain origin, which is the latent representations, and their domain origin is represented by the domain labels indicated from which domain this representation is coming. And we particularly enforce some constraint on this mutual information, and these 2 constraints. The first one is the expert demonstration constraint. We said that this mutual information should be less than 1 bit. And then this helped the invariant discriminator just to focus on the information regarding the goal completion levels, but disregard the information related to visual differences between the expert and agent domains. And another constraint that we introduced is prior data constraint. And this is implemented in a way that we collected data from experts and agents domains when they were doing random behavior, but not particularly attempting a particular task or performing a particular behavior. And under this assumption, we assume that in this case, since they are not performing any goal, the distribution of this observation should approximate the match. And in this case, the mutual information should be close to 0 because there is no goal completion in this scenario. And this also helps us to use it. This is another additional learning signal regarding the information that should be thrown away by the preprocessor. So this is the high level of description summary of this mutual information constraint, and Edoardo will be presenting details in the second part. So once we obtain the regularized discriminator, we can combine it with an RN algorithm. In this case, we combine it with Policysoft actor critic algorithm, and then we designed 6 different environments in Mujako to evaluate this algorithm. So as you can see in the above figures, that these environments involve like low-dimensional control task, which is richer, and the inverted pendulum, and then as well as it is consists of some high-dimensional control tasks, as you can see here in the below. And also, we also introduce differences in terms of environment appearance and the agent embodiment in both expert and agent domains. So I would like to summarize some takeaway points from the results. So first, our results show that DisentanGAIL can really effectively solve the observational imitation learning problem in low-dimensional control tasks. And as you can see, it is outperforming the state-of-the-art approach, which is proposed by Cetin et al. Significantly, even if this approach is provided 5 times more experience. But most importantly, we can also clearly see the benefits of using regularization. For example, if there is no differences between agents and expert domains, we can see that DisentanGAIL, the full algorithm, and without the regularization, they perform equally well. But when we start introducing differences between these domains, we can see that the algorithm without regularization starts to perform really poorly in these settings, whereas the DisentanGAIL, the full algorithm, can maintain its performance robust against different combination of differences. So another thing that we already said that we also test whether this algorithm can be scaled to high-dimensional control tasks, and again, our experiments show that these methods can really perform well as compared to the state-of-the-art methods. And again, we can here clearly see the benefits of using the regularization, the mutual information constraints, to make this algorithm to work well in high-dimensional control tasks as well. And also, you might say maybe we might not be able to collect prior data always, and in this case, even as you can see, even we don't use the prior data constraints, the DisentanGAIL algorithm can still be able to perform well in these high-dimensional control tasks. So I am going to stop at this point, and I am going to hand over Edoardo to talk about the details. But before that, I would like to also mention that we also have a project starting soon, and we will be exploring this idea how we can map to transfer the human-human interaction to human-robot interaction settings.
So thank you very much, Oya. Can you see my screen?
Yes.
I guess on my side there were a few issues when you actually presented. I don't know. I hope it wasn't the case for everyone, that the screen started to come on and off, but hopefully it won't be the case for the second part of the presentation. So again, thank you very much, and yes, in this second part, I will talk about the details of our method. Therefore, going back to our algorithms methodology, and also delving deeper about its implementation details and relative motivation. So, going back to our algorithm, as Oya mentioned previously, we propose to split the discriminator into two main submodels. So the first submodel being the preprocessor, which will take the form of a neural network outputting the parameters of a Gaussian distributions, which samples should ideally represent a domain invariant space, thus discarding domain-specific features coming from the observations that are then used to compute the pseudo-reward. And the second model being the invariant discriminator, which is instead a neural network taking as input the latent representations of the 4 most recent observations at any given time step to output the discriminative score. The reason why we input a concatenation of latent representations is so that the discriminator can overall make its classification decision based on goal completion progress from the portrayed behavior. Yeah, of course, then the main idea is to enforce constraints on the mutual informations such that it effectively represents a domain invariant space. So, hence, we propose to enforce, of course, two constraints between the latent representations outputted by the preprocessor, recapping, and the domain labels of observations, where, again, domain labels are simply binary labels specifying whether the observations, where each relative observation was collected by either watching the expert or the agent act in its own domain. So in this case, the domain labels di for each observation oi, with, of course, its latent representation zi. And the mutual information is estimated utilizing a statistics network and derived utilizing actually the Donsker-Varadan dual representation of the KL divergence between two random variable distribution. We refer to their work for further details on this method. So the first constraint that we want to enforce then is between the set of expert demonstrations. So from observing the expert demonstrate the objective, and the current set of agent-encountered observations. So while the agent is still attempting to perform the task in its own domain. And particularly, we propose to constrain the amount of mutual information in the representations from the observations in these two sets to be less than 1 bit. And we will explain why later on. We also propose to enforce a second constraint, this time between two prior sets of data, as Oya mentioned, collected independently by watching both agent and expert act in their own domain, while neither is particularly attempting to accomplish the target goal. And in this case, we propose to constrain the amount of mutual information to be approximately 0. So first of all, then I will try to give a bit of a deeper intuition behind this constraint. Well, the task of the discriminator in our setting is to effectively classify expert demonstrations accomplishing the task from agent observations, still in the process of learning the task, in order to assign high discriminative scores to the expert demonstrations that show task accomplishments, and therefore high pseudo rewards to the expert demonstrations, while low pseudo rewards to the rest, such that if the agent is then trained to maximize the obtained pseudo rewards, ideally it would bring its behavior closer to the experts. To perfectly make such classification decision, therefore, our discriminator requires exactly 1 bit of information. However, we do not want to rely on domain information, which is uninformative about what is the behavior needed to achieve a demonstrated goal. And instead, we ideally want to rely on goal completion information, encoding the progress that each observation shows towards accomplishing a target goal, no matter in which domain the observation was collected. Hence, enforcing the expert demonstration constraint with the mutual information between the latent representation and domain labels to be less than 1 prevents the discriminator to make its classification decision solely based on domain information, and instead forces it to seek goal completion information to fully maximize its objective. Similarly, for the prior data constraint, as we are utilizing two sets of data where the goal completion levels are expected to be approximately independent of the domain origin, enforcing the prior data constraints effectively specifies that the distribution of features in the latent representations between the observations in the two prior sets of data should be approximately equivalent. So therefore, now we will delve a bit deeper into the details, let's say, of our model and our proposed architecture and optimization. So practically, we enforced both expert demonstration and prior data constraint, utilizing two auxiliary losses for the preprocessor's parameter, where specifically the expert demonstration constraint is enforced through an adaptive penalty loss term, L beta, that is simply utilizing a weighted estimate of the mutual information, where the weight is adaptively increased or decreased based on the current estimate on the mutual information and an hyperparameter, Imax, that quantifies the maximum amount of mutual information that we allow our latent representations to retain. And yeah, in this case, we simply increase the coefficient beta if the estimated mutual information exceeds such parameter, and instead we decrease our coefficient beta if it's less than half of this parameter. Instead, for the prior data constraint, we utilize another kind of penalty, particularly a dual penalty, where this simply corresponds to the weighted difference by a weight lambda between the estimated mutual information together with the estimated mutual information and the maximum constraint value that we allow our latent representations to retain. Where in this case, the parameter lambda is updated at every step, approximating dual gradient descent. In the first case, we utilize, in practice, Imax is equal to 0.99. And in the second case, for the prior data constraint, we utilize Imax is equal to 0.01. So reflecting the values of our constraint. But then going into a bit more details about the nature of prior data, the observations in the prior sets of data are obtained by watching both expert and agent, while neither of them is particularly performing the target task. In practice, we collect this data simply utilizing random rollouts in both expert and agent domain versions of the environment. And thus, given that here the domain labels should be approximately independent of the goal completion information, we can enforce much stricter constraints to reflect these characteristics in the latent representations. Also, we would like to point out that, as shown in the experimental results introduced by Oya also before, prior data is also not essential for DisentanGAIL to work. And our algorithm can recover good performance in most problems with only the expert demonstration constraints. However, it does help, especially in the cases where we have more prominent domain differences between the agent and expert environment. So regarding the model structure, the preprocessor, in our case, takes the form of a simple convolutional neural networks, where we will give the specific details of the architectures later on. Where particularly the output of this network is flattened into a k-dimensional vector, and used to compute the parameters of the normal distribution, where particularly the first half of the variable is used as the distribution's mean, while the second half of the variable it's first scaled into a predefined positive range, and then diagonalized to represent a diagonal covariance matrix. This scaling that we perform not only serves the purpose of making all the covariances strictly positive, otherwise we would get degenerate solutions, but it also the scaling here, for example, by using a tan h nonlinearity and then dividing the exponentiation by 2. We found that empirically it constrains the covariance to be in a good range, if you want, and also around 0.5 at initialization. That we found was something that actually played a concrete impact on had a concrete impact on performance, surprisingly, scaling the covariance appropriately. Instead, the invariant discriminator, statistics network, and policy are simply just fully connected neural networks, which we will specify their structures later on. So regarding the discriminator optimization, the main loss term for the discriminator, as in most inverse reinforcement learning specifications, it's simply a standard cross-entropy loss, where we also found it beneficial to augment the two terms of the cross-entropy loss. So in this case, pushing up the probabilities of latent representations in our expert demonstration sets, and pushing down the probabilities of the observations collected in the agent observation sets by a third term that pushes down the probabilities of the observations in the prior data sets, hence utilizing the prior data as additional negative examples, so examples that do not show task accomplishments. We found this to be slightly helpful also in further bolstering the performance and robustness of our method. Thus, the discriminator is overall trained to optimize this cross-entropy loss, augmented by the relative penalty terms that were introduced for constraint enforcement. So for optimizing the policy, we instead compute the pseudo rewards. So utilizing, in this case, a deterministic version of the discriminative score, where we simply concatenate the means of the latent representations rather than the latent representations themselves, such that we keep the learning signal for the policy deterministic, and then simply compute the pseudo rewards as the discriminative score as outputted by the discriminator from this deterministic latent representation. A parameterized policy then is optimized with the soft actor critic, as mentioned by Oya, which simply corresponds to maximizing the expected sum of encountered pseudo rewards discounted by the entropy. And this, we refer to the main paper for details, but this has the effect of trying to find an optimal policy that also acts as randomly as possible in the environment, and ideally is therefore also as robust as possible in achieving the target goal. So to optimize the statistic network, we make use of the mutual information neural estimator by Belghasi et al., where we simply train the statistic neural network to maximize its expected estimated information with respect to the possessed data. However, there is a problem with this formulation, and this problem is that if our statistics network gets temporarily stuck to a local minima, because we have that the latent representations are not fixed components in a data set, but rather change throughout optimization, what can happen is that our discriminator structure and our preprocessor with the invariant discriminator can attempt to conceal information into the latent representation, conceal domain information into the latent representation without the statistics network noticing it. So the discriminator can be incentivized to fool the statistics network rather than minimizing the amount of domain information present. And in order to counteract this, we propose two further techniques. The first one being a double statistics network, which entails learning two different statistics networks independently from the data, and then simply estimating the mutual information as the maximum estimate between the two statistics network. And this practice has the advantage that if a statistics neural network gets temporarily stuck in a local minima, it has the time to recover without affecting the mutual information estimates. And secondly, also, it consists in applying the spectral normalization operation to the layers of the invariant discriminator, which effectively constricts their expressivity, hence making it harder for the invariant discriminator to recover mutual information about the domain label that were initially missed by the statistics network, which are instead unconstrained. So here we show our overall optimization procedure. Given that I believe we do not have, we are running a bit out of time, I will maybe skip the details about the optimization procedure, but it's outlined in the algorithm and also in the main paper. And then talking about the evaluation, we again evaluate our method in 6 different environment realms based on commonly used Mujoko benchmark environment, where each environment realm simply corresponds to a set of environment with a shared semantic goal, but with the significant differences in terms of both agent embodiment and environment appearance. And yes, we compare the performance of our algorithm with the different baselines, such as previously proposed solution as third-person imitation learning and various ablations of our method. So in particular, for the inverted pendulum realm, we describe domain differences consisting in both the number of links of the agent together with the color appearance. For the richer realm, we consider both changing the amount of links of the agents together with the tilting the camera, and therefore changing the appearance of the observations. For the Hopper and Afchita realm, we consider differences both about the coloring of the agent, but also involving the number of actuable joints. As for example, we lock the fit joints or add an additional tie joints in the Hopper realm. And also in the pusher and striker realms, we consider differences involving the link sizes together with the agent appearance and their structural configurations. To produce the observations that then are used from the discriminator to compute the pseudo rewards, we render the Mujoko environments at different time steps, and subsequently we rescale the dimensionality of the observations to make them as small as possible while still keeping all the relevant details visible. So we vary different parameters about the network architecture with respect to the perceived difficulty of the different realms. However, we also observed that DisentanGAIL can work with different networks with the varying expressivity, and therefore fine-tuning of these parameters, while it's definitely useful, it's not essential in most cases. Where all of the architectures are very simple architectures, as in reinforcement learning usually. See, the simpler the architecture, the better the final performance. Unlike in other areas, in other machine learning areas, such as maybe supervised or unsupervised learning and computer vision, where many times adding complexity can lead to better results. So in this case, the convolutional preprocessors are simple concatenation of 3x3 convolutional layers, followed by tanh, nonlinearity, and max pooling, where we increase the number of filters as we go down the architectures, but we decrease the spatial dimensionality as we apply the max pooling. And the invariant discriminator and statistics network are simple, fully connected neural networks with ReLU nonlinearity for the statistics network and tanh for the invariant discriminator. And here we also show the buffer sizes used. So this is, for example, the number of observations BE, or the numbers of the number of observations contained in prior data used to solve the task. And we believe this quantity can likely be further diminished without hurting the performance, as this was not one of the main focus of our method, to try and learn behavior with as little demonstrations as possible. But overall, given that most of the demonstrations were collected through multiple very similar rollouts of a single trained agent, we believe that having even smaller number of rollouts can perform a similar ultimate performance as the one displayed. So experimentally, as Oya showed, our method is both able to overcome domain differences consisting in environment appearance and embodiment mismatch in low-dimensional problems, together with the scale to high-dimensional control tasks, overcoming major differences in domain appearance and embodiment, while most other algorithms fail. So once again, showing the effectiveness of our method and the difficulty of performing observational imitation in high-dimensional settings. So some additional results is that one thing is that we check whether the proposed mutual information constraint successfully guide the latent space to represent to be a domain invariant space and represent domain invariant features. And to examine this, after performing an experiment with DisentanGAIL, we sample in each environment realm 8 different observations from the agent domains. We compute their latent representations and match them with the closent representation, with the closent observations in the expert domains in terms of the L1 distance of their latent representations. And we can see that in the 6 environment realms, the produced matchings actually reflect observation similarities in terms of semantic features which are invariant of the domain origin, but instead contain information about the goal completion levels of the observations. So particularly, as an example, for the inverted pendulum realm, they appear to contain informations regarding the angle between the inverted pendulum's cart and the end effector, independently, for example, of the number of links or the color. Or, for example, in the half cheetah and hopper realm here, they appear to encode the relative position of the agent with respect to the floor tiles. Hence, that by feeding then 4 consecutive observations into the invariant discriminator, the invariant discriminator would be able to assess whether the agent is advancing throughout consecutive observations, and can thus reward behavior that show the agent advancing in the desired direction. So some particular other ablations that we consider that we believe are particularly insightful is, for example, enforcing tighter expert demonstration constraints. For the expert demonstration constraint itself. So enforcing tighter values for this constraint by utilizing lower value of the Imax parameter for the adaptive penalty. And while doing so, ideally pushes the preprocessor to further discard the domain information that the invariant discriminator could exploit. There is an issue with doing this. And the issue is that in the expert demonstration set and in the set of agent observation, the domain labels are very much correlated with the amount of goal completion information contained. As while the expert demonstrations show task accomplishment, therefore should contain high, let's say, goal completion, high values for the goal completion information, the agent that is still in the process of learning the task should contain instead the low values for the goal completion information. And thus, the domain labels themselves are correlated also with the goal completion information, and not only with the domain origin of the observation. Thus, enforcing tighter constraint has the unwanted side effect of also pushing the amount of useful goal completion information containing to the latent representation down. And we show this by estimating the amount of mutual information between the latent representation and the true environment rewards, so the default environment rewards, the one that are used traditionally to solve the semantic goals. And what we observe is that, in fact, by pushing this constraint hyperparameter down, the amount of mutual information about the true rewards contained into the latent representation decreases drastically. And this is reflected then also on the final performance, as we show that tighter constraints lead to suboptimal performance in the various environments, in the various low-dimensional environments. We also perform some further experiments, as for example, here we ablate the effects of our domain information disguising prevention techniques, such as removing the double statistics network and the invariant discriminator regularization, and confirm that both practices positively impact the performance. And we also test with varying not only the agent appearance and the agent embodiments, but also by varying elements of the environments that do not involve the agent itself, but instead involve irrelevant features such as the background. And what we observe is that in both environments here where we tested this, while the DisentanGAIL agent is still able to recover very close to the expert's original performance, the final performance appears to converge in an increased number of iterations. And this is especially evident, for example, in the Hopper experiment that was performed here, where, of course, as shown also by the previous visualization about the observations matchings, the invariant discriminator appears to encode information about the tile's relative position with respect to the agent into the latent representation, which now, by making the background harder, by making the background darker, are harder to discern, thus reflecting these characteristics. However, overall, DisentanGAIL appears to work even when drastically changing such spurious features about the different environments. So in conclusion, therefore, we show that while observational imitation might appear as a majorly ill-posed problem, it is solvable even for high-dimensional problems themselves. And particularly, our work shows the effectiveness of mutual information constraints to guide the learning process, and overall also narrows the evaluation gap with the more traditional agent-centric imitation learning problem, where the agent, instead of being where the agent and the discriminator, instead of being provided with only visual observations of an expert performing a task, is instead provided a full set of both states and actions of the expert performing the task directly from the agent's point of view. And ideas for future works include extending our algorithm with both data augmentation strategies, but also by incorporating information from multiple related tasks in order to recover priors for better disentangling, let's say, goal completion and domain information from the demonstrations. We provide implementation of all our algorithms and environments, and also to get additional information about our work, please check out our paper here at this link or QR code, and feel free to reach out to either me or Noia. Well, thank you very much for the attention, and let me know if you have any further questions.